Hello everyone. First of all, I would like to thank for this opportunity online presentation. And this time I will give you a comparative life cycle assessment of linear LED designs developed in the ReproLight project. My name is Victor Ferreira and I am in charge of the environmental LCA and sustainability studies in the IREC, the Catalonia Institute for Energy Research. The ReproLight is a European research project which objective is to support the European lighting industry for a sustainable and competitive future. There are several actions involved in the ReproLight project, as you can see in this slide. The main actions are focused are in three aspects. The first one is the sustainability and circular economy. The second one is the modularization of the luminaires. And finally, the smart production scheme. The project is under the program Horizon 2020 with a total funding around €4,300,000. And its duration is of 4 years, expected to finish in this September 2020. The consortium is constituted by 4 European countries, as are Austria, Germany, Italy, and Spain. And the involved partners are experts in industry, lighting, manufacturing, communication, and sustainability. The Energy System Analytics Group in IREC is in charge of the life cycle assessment, which support the eco-design and circular economic strategies in order to enhance the sustainability of projects which are executed in this entity. The life cycle assessment is a tool that allows to quantify the impact of a product throughout its life cycle, including raw material extraction, manufacturing, use, and end-of-life stage. The LCA methodology is based on the life cycle thinking approach, and it is supported by the ISO 14014 and 14044. The LCA methodology has 4 phases. The first one is the goal and scope definition. The second one, the life cycle inventory. The next one is the life cycle impact assessment. And finally, the interpretation of the all results. The interaction of these phases allow us to inform decision or policies that aim to reduce the life cycle impact of a product. The life cycle assessment applies for product development and improvement, strategic planning, public policy making, marketing, benchmarking, eco-labels, and product declarations. So we move to the comparative environmental LCA for the ReproLight LED luminaires. We start with the goal and the scope definition, which is the first phase of the LCA. Here, the objective is to compare the life cycle environmental impact of the LED luminaires in ReproLight versus the LED benchmark to be used in an industrial setting. We address several aspects as the environmental analysis of materials, lighting regulation in industrial setting, serviceable luminaire, and electricity mix scenarios. We use for this study this kind of the luminaires. The first one is the N-line configurable, named as luminaire A1. The second one is the N-line exchangeable luminaire, named as luminaire A2. And the benchmark luminaire, which is named as luminaire B or LB. The functional unit is used to refer all results in order to obtain better comparison. It was defining a lighting system for an industrial hall constituted by 369 luminaries with a luminance of 300 lakhs, and the lifetime use was 70,000 hours. The cradle to grave was the approach used in order to define the system boundaries. We include here the raw material extraction stage, the production of the components of the luminaries, the assembly stage, transport for installation, uses phase, transport to disposal, and finally the end of line of disposal. Regarding the life cycle inventory, we use foreground data, which involves bill of material for each component in the luminary. In addition, assembly energy consumption from luminary manufacturing and calculate usage phase energy consumption. We use other kind of data as background data, which involves datasets from LCA database for production of each component in the luminary scaled to quantify the bill of materials. In addition, we use datasets for waste management. Here we can see the classification for the life cycle inventory in terms of material. We consider mechanic parts, LED control, wires, optics, LED module, and lighting system dimmable. We can see here the main difference of reprolite luminaries respect to benchmark luminary. We consider here the reduction of the steel in 9% and reduction of plastics in 70%. The number of the LED model was reduced too, and the amount of the LEDs in terms of the mass was reduced, and these LEDs are free of gold. We consider the plugs or connectors for exchangeable LED model in order to study the exchangeability scenario. For the life cycle inventory in the usage phase, the main focus is the energy consumption considering dimming. Here we can see the difference is that lower energy consumption in reprolite luminaries when it is compared with the luminary benchmark. The lighter contour is used in the model. It tries to keep the luminance on the working place constant, taking into account the natural light entering through the window. This allows the reduction of the LED temperatures, which leads to reduce the degradation rates. In consequence, we have energy saving and elongation of the lifetimes of the luminary. For the end-of-life stage in the disposal scenario, we use the best practice according to the waste electronic equipment of the European Directive for all material which conform to the luminaries. For example, for the ABS and PMMA plastics, we consider the incineration processes. For the rest of the material, we consider the recycling processes. For the life cycle impact, we consider these environmental impact metrics in order to study the behavior or the environmental behavior of the reprolite LED luminaries. As you can see in this table, we have the global warming potential, the primary energy potential, abiotic depletion, which is divided in abiotic depletion potential elements and abiotic depletion potential fossil. Other metric is the acidification potential and eutrophication potential. So we move to the main results obtained in this part. In this case, we have the life cycle assessment of the luminaria benchmark. And we can see in the left side the overall performance of this luminary for the production, usage phase, and end of life. The usage phase has the highest contribution for almost environmental impact categories, as you can see in this figure. In addition, the production stage and end of life has lower environmental impact for this is environmental categories. But if we look the ADP element, the category, the ADP element, we can see that production state has higher environmental impact, around 75%. If we move to the right side, we can see the ADP element by component, and we can see the percentage for this. And the LED model has the higher contribution, around 75%. Other component is the LED contour, which shows 30%, 13%. So we have mechanics in 5% and wiring in 7%. In the case of the LED model, we can see the contribution is because we have here several parts in the LED model as LED board and LED, which contribution is more or less the same. So this is results allow us to define linear lighting configuration that can lead to use less amount of component and energy saving. So we can see here in the left side the life cycle assessment of the luminaria A1 considering dimming. You can see that the distribution of the environmental impact is very similar to the behavior of the luminaria benchmark. For example, the usage phase is still continual, has the higher environmental impact in almost environmental categories. But the production state has now lower environmental impact in the ADP element, around 60%. If we go to the right side, the comparative LCA of the luminaria A1 and luminaria benchmark, we can see that the luminaria A1 has better environmental LCA than the luminaria benchmark, decreasing the impact around 27% for all categories, except to the total ADP that was reduced at 53%. If we see the ADP category, we can see that the LED model impact is reduced considerable, around 80%. This is because the number of the LED model was reduced and we use less amount of coal. The luminaria A1 with dimming has a rate reduction in the usage phase around 26% due to the energy saving because the daylight contour in the dimming. If we see the contribution percentage by components in the right side, we can see that now the LED module and LED control in the luminaria A1 have now 37% and 33% respectively. So we can see that from these results, the environmental benefits of the ReproLight luminaria is very good compared to the luminaria benchmark. Now I will give you the results for the serviceable luminaria. In this case, we use two scenarios. The scenario one is about no exchangeable LED model using luminaria A1 for a lighting system. The second scenario is using exchangeable LED model. It is important to mention here that we include a new stage for spare parts. You can see this stage in the left side. Yeah, and it is in order to define the new system boundary for the scenario one and the scenario two. We assumed that the LED module and LED control are designed to work along the lifetime of the luminaria according to available data. We consider here a failure fraction of 1%, a quarter attributed to the LED module, and 3/4 attributed to the LED control. For the LCA of the scenario 2, we consider the plugs materials in the LED model, but the materials for the other components as LED control, mechanics, optics, etc. are as in luminaire A1. The energy consumption was considered the same for both scenarios. So here you can see the results for the ADP element for these scenarios, and we can see there are not a radical difference between them. So if, for example, we remove the usage phase because the consumption of the electricity is the same, we can see that the luminaire production stage increase around 0.4%, which is due to the plus. This is a little increase. But, for example, the production spare parts of the scenario 2 is reduced at 31% since the one LED motor is replacing an industrial lighting system instead of one full luminaire in the scenario 1. Even if we make some variation in the percentage failure fraction, we can see low benefit in the relative total impact when the percentage failure fraction is increased. So we can see that there is not a big difference between both scenarios with include the exchangeable LED model. Other important scenarios that was studied is the electricity mix. As mentioned before, the usage phase has the higher environmental impact in the life cycle of the luminary. So this is important to study the overall environmental LCA performance for the luminary. In this case, we use the luminaria A1 comparing different electricity generation source. We consider different countries as Sweden, France, Spain, Italy, and the baseline, which is the European 28. So we can see that the use of the electricity with higher contribution of renewable energy source as Sweden brings important impact reduction in the categories as abiotic depletion potential fossil, acidification potential, eutrophication potential, and global warming potential. However, this electricity mix is not free to other type of the non-renewable energy source, such as the nuclear energy, besides the use of non-renewable elements, which contribute directly on the abiotic depletion elements and primary energy categories. In contrast, if we see the Italy scenario is higher in abiotic depletion potential element and abiotic depletion potential fossil because the use of the non-renewable elements results, for example, antimony, chromium, copper, and natural gas as non-renewable energy resource, which also makes the global warming potential and primary energy slightly higher due to the natural gas and coal heart. So what are lessons learned so far? Well, in the production stage, we have important lessons regarding to the optimization of time of size of the components. For example, a reduction of the materials, reduction of the printed circuit board, of the area of the LED modules, and using of less amount of the precious materials as, for example, the gold. In case of the exchangeable LED model, it is necessary to make more efforts in order to reduce the impact, in order to achieve the environmental benefits. In the usage phase, we achieve higher efficiencies due to the dimming, but it is necessary to consider the renewable energy source for the electricity consumption. In addition, it is important in order to increase the environmental impact reuse the LED model. In the disposal or end-of-life stage, it is necessary to meet recycling targets and technological development in order to increase the recycling and the percentage of recycling rate. And in addition, it is necessary to consider the economic aspect in order to obtain the balance between the environmental impact and the economic implications. So this is lessons allow us to suggest eco-design strategies. For example, they reduce the amount of the virgin materials, in particular critical materials, or use recycled material as much as possible. In addition, easy exchangeability and upgradability. And finally, to bring together manufacturers and waste managers to create guidelines for easy dismantling, material separation, and recovery in the end-of-life stage. Finally, I would like to share with you the challenges of the application of the LCA for eco-design and circular economy for LED products or luminaires. Characteristics such as repairability, easy dismantling, upgrading, reuse, and recyclability differ between luminaires. They are going to significantly affect the useful life and directly affect the manufacturing and usage stage. Moreover, also the end-of-life stage has less relative impact in the total impact of LED luminaires. Some of these characteristics also affect the assessment of this life stage because luminaires that are easy to dismantle and are highly recyclable should have lower impact at the end of life. These characteristics should be considered as much as possible in future LCA studies to evaluate the eco-design and circular economic strategies from environmental point of view. Therefore, it is necessary to have access to factual data to provide valid, accurate, and reliable LCA comparative results between LED luminaires. So this is all from my side. If you have any question, please share them. And thank you very much for your attention in this online presentation.